So I've structured this talk so you could follow most of it even if you're not too familiar with neutron scattering. And I also try to include a science case for neutron scattering. So apologies to those of you for whom that's old hat, but I think it's important to give the context for why this is something that's worth spending time and money on. So thank you for the introduction. What can I add to what you've already said? Not so much. My previous job was at the ILL in Grenoble, which is the currently leading neutron facility in the world in terms of scientific output. It may not be the most intense in terms of its neutron beams anymore. That's probably been taken over by places like SNS and JPARC in the US and in Japan. But in terms of scientific productivity, number of papers, ILL is still head and shoulders above anywhere else. So I moved to ESS back in 2010, which makes me one of the really old guys there. There were about 30 people working at the ESS then, and now we have about 600. And as Dimitri mentioned, I'm also adjunct professor at the University of Copenhagen since 2012. So, a bit of history. Neutron sources. Okay, 1932, discovery of the neutron. That was the first neutron source, right? James Chadwick was able to establish that there was such a thing as a neutron by bombarding beryllium with alpha particles, and out came this new kind of radiation. So the first neutron source, if you like, 1932, 1 neutron per whatever unit you want to invent, and this is neutrons per square centimeter per second. That's a typical flux unit, and it also gives you an idea of the size of neutron beams. They're typically measured in square centimeters. So 1932, 1, on a log scale, the neutron facilities or neutron sources improved pretty quickly over time, with working initially with naturally radioactive isotopes, and then working on with the first accelerator-based cyclotrons. And then what happened, of course, around 1940 was the discovery of nuclear fission. Here you can see a picture of the Chicago Pile 1 in the squash courts at the University of Chicago. You have a nucleus, a magic nucleus, not just any old nucleus. It's got to be a special fissile material, right, like uranium-235. 1 neutron comes in, it splits, it releases heat, and it produces more neutrons which go on to split more nuclei. That's the famous chain reaction. And that led to a huge increase in the brightness of neutron sources which were available during the 1940s. But you can see already by the 1960s it's pretty much plateaued. And it culminated in the constructions of places still running today, the high flux isotope reactor at Oak Ridge in Tennessee and the ILL in Grenoble in France. Very similar neutron fluxes in there. And if you look further up to today, the Forschungsreaktor, the research reactor in Munich, is basically no brighter than HIFA or ILL. So in terms of nuclear reactors, we've reached a plateau which basically comes from our inability to extract the heat quickly enough. You get a lot of heat emitted in a fission process, which is great if you want to produce energy. It's not great if what you want is more neutrons. So you get this problem of heat density, which is insurmountable technologically. You could perhaps gain another factor of 2 or 3 if you work really hard, but you're not going to gain another order of magnitude over that. So what came along in the 1970s, 60s also, if you want to look at the early work, was nuclear spallation. So spallation is a nuclear process where you take a proton. It doesn't have to be a proton, it could be a neutron as well, any particle, but it's much easier to accelerate a proton, obviously. And you collide it with a heavy nucleus. The heavier the nucleus, the more neutrons it's going to emit. And it can either evaporate neutrons like that, with the nucleus more or less staying intact, or it can decompose, looking like a fission process, and emit neutrons as well. And this you can do with any heavy nucleus. It doesn't have to be a magic uranium-235. It could be tantalum, tungsten, lead, uranium, anything you like. The heavier it is, the more neutrons it has to emit. And once this process was controlled, we were able to go above this fundamental limit which the reactor sources were stuck at. And so until the present day, the 2 brightest spallation sources today are the spallation neutron source at Oak Ridge and the Japan Proton Accelerator Research Complex at Tokai in Japan. And ESS plans to be about an order of magnitude brighter and come online, well, not exactly 2020, but I didn't want to show it outside the X scale of this plot. So the idea is the ESS, when we come online, we are going to be the biggest, best, brightest, and so on neutron source there is. So neutrons they are special. I mean, there's a reason why you bother with neutrons. You have to mine the neutrons out of a nucleus, so they are expensive and difficult to get out. The reason why you bother is because they have all these great properties which allow them to be a really useful probe of solid-state materials. They're deeply penetrating, they interact with the nuclei, not with the electron cloud around the nucleus like X-rays do. They have a spin, so they probe the magnetism directly. They're also inherently interesting themselves. They decay. They have a 1/e time of about 900 seconds, which means you're able to study the weak interaction with neutrons. And because they're heavy, when they are thermalized, i.e. they're slowed down to room temperature motions, they move pretty slowly. They also have this amazing property that they're easily visible. Materials, here you're seeing water, right, through aluminium, and it would look the same if it was through steel. That's very hard to do with many other probes, right? And the reason why you can do this is if you look at the mass attenuations, that's basically the cross-section, as a function of the element number, it looks like a random scatter plot, as opposed to what it looks like with X-rays. This straight line, this is the log scale. So it means that you're able to look at materials which are, let's say, right next to each other on the periodic table, and they will have very different scattering cross-sections, be easily distinguishable. And you can also look at heavy elements and light elements next to each other in the same system and be able to see the light element and not be swamped by the signal from the heavy element, right? Which is why, for instance, you could see the coffee in the percolator. That would be impossible to do with X-rays. The other trick you can play with neutrons is something called contrast variation. It's about being able to see a signal over a background and where you can play around with the background. So you can play around, because it's the isotope, that it's a nucleus you're seeing, so hydrogen and deuterium are completely different, whereas chemically they are basically the same. So if you have a system, let's say proteins, and you want to measure the proteins, and the proteins happen to be sitting inside a matrix of something else which you're not interested in, you can cancel out the signal from the matrix by mixing in the right mixture of heavy and light water around it, and you just see the thing that you're interested in. This is a tremendous strength. Again, it's something which really plays to the strength of the neutrons compared to X-rays, particularly in organic materials and biological materials. I mentioned they have a magnetic moment. This is obviously important for looking at magnetic structures. Here's a picture of an iron arsenide superconductor. The superconductivity and magnetism are very closely related. I'm going to come back to that later on. Neutrons have been essential for our understanding of superconductivity by probing the magnetism, which correlates with it. They're also very important for looking at the position of hydrogen. This is a detail of an active site in a protein, and X-ray protein crystallography has become a huge business. There have been several Nobel Prizes in that over the last 10, 20 years. What X-rays have a lot of difficulty doing is seeing the chemically active sites, which usually means swapping over protons, hydrogens from one position to another. And neutrons can see that very, very easily, again, because hydrogen is so visible with neutrons. And we're not bothered by the presence of heavy elements nearby. As I mentioned, very good for magnetism. Magnetism and superconductivity are very closely related. In particular, the interplay, the coupling between electrons, which are responsible for superconductivity, is mediated by vibrations. And so neutron excitations, which measure these vibrations, are critical for understanding the mechanism for superconductivity, particularly for high temperature superconductors, which have a lot of promising technological applications. So the science case for neutrons is basically the science case for materials science. Right? In a previous talk, I used to have a slide saying that the Stone Age didn't end because we ran out of stones. It turns out that's actually not exactly true. the particular stones that were needed for making stone tools were actually quite rare, and there was a real big trade and business going on in trading the particular kinds of flint which were needed for stone, so I took that slide out. But I like the idea. Material science is the basis for most of the technological progress that we've made over the time of human civilization. And so you almost don't need to make the science case for material science, except you really do, because it easily gets forgotten. So, back to the ESS. So this is actually an old project. I first got involved with the ESS back in 1999, when there was a proposal to build it, and we hadn't decided where it was going to be, but it was going to be this fantastic new thing, and we were all designing instruments for it, and it totally flopped in 2002. We failed to get it funded. It basically died as a project back then. And it was revived shortly after that, when a group of European labs got together and decided, okay, that failed, let's find a way to actually make it work. And we decided the way to make it work was to first decide where it was going to be built and who was going to build it before arguing over getting the funding. Because we looked like we were all out fighting each other, right? We were not a collaborating community back in 2002. So there was a lot of political progress made between 2003 and 2009. Which resulted in 2009 a decision that, yes, if we build the ESS, it will be built in Lund in Sweden. Right? That was a community that got together. And then we basically succeeded in getting the construction funding between 2012 and 2014. So 2012, that was when we wrote the technical description of what the ESS should look like. That was the design update phase, updated from the 2002 version. We had a ceremony where the Danish and Swedish research ministers turned up with shovels and dug a hole in a field in southern Sweden, and that was formally when the construction started. We officially start our initial operations phase this year. That was because back in 2012 we thought we would have first protons on target and first neutron beams in 2019. That's not going to happen. We haven't yet finished installing the accelerator. It's going to be another 3 years. But it didn't stop us declaring that we're in initial operations, because they've turned on the accelerator for the first time, or the first few meters of the accelerator anyway. But we will be starting a user program, i.e. producing science, in 2023, and by 2025 is when we formally declare the construction project complete, which doesn't mean that we finish building ESS. It means we've run out of construction money, and anything else we want to build, we have to spend from operational money. So this is the scope. We wrote a technical design report back in 2013, which describes the technical boundary conditions, right? So it's a proton accelerator. It's going to be the world's highest power proton accelerator, 2 GeV, 60 milliamps, with a frequency of 14 hertz. So at 14 times a second, you get a pulse of protons with that energy, and that current hitting a target, and a pulse length of roughly 3 milliseconds. We have a target consisting of a large rotating wheel of tungsten, and the idea is very similar to that of a rotating anode X-ray. Right? You just want to distribute the heat over a larger volume or larger area so you can cool it. So we have this 2.5 meter diameter tungsten wheel, which rotates at about half a hertz, so it takes 2 seconds to do a full rotation, and the proton beam hits the edge of the wheel 14 times a second. So a 5 megawatt time average power. And if you work out the numbers, you can see that's about 125 megawatts peak power when the proton beam is on. And we're committed to building 22 instruments, neutron beamlines, public, meaning that they are available to the user communities in the countries that have paid towards building ESS. And it will be operating 200 days a year. It's a single-purpose user facility. It's not, doing something else at the same time which allows us to produce science. It is a scientific facility. That is our raison d'etre. We have 2 host countries, Denmark and Sweden. And so the facility itself is in Lund in Sweden. Here you can see Malmö and Copenhagen, Denmark and Sweden. They're connected by a bridge, and the data management and software center sits in Copenhagen. That is the Danish host part of the ESS. It's a political construct in the sense that Denmark and Sweden have a different status to all the other partner countries. But it's a very useful thing because it means that software is not going to get scrubbed like it does in many, many other projects. When you realize you're starting to run out of money, you think, oh yeah, we'll have fewer programmers and we'll build some more stuff instead. And then you realize you can't do anything with the stuff because you haven't got the software to run it. So we have this agreement which has ring-fenced the amount of resources that we're putting into software, which is really critical for this. And physically, though, that facility, the hardware will be sitting in Copenhagen and with a fast fiber optic link over to us. Please.
Helium for?
Sorry?
What's the helium cooling for?
The helium cooling is to take away the 5 megawatts of heat which arrives on the target. So the target absorbs 5 megawatts of heat. Sorry, no, it's helium gas. Sorry. So you have tungsten being heated to a fairly high temperature, and you have a flow of helium gas going through and taking away that heat. We had 2 alternatives. It was helium or water. Helium is much less reactive. That's why we chose it. Even though, of course, the specific heat is much lower. It's not liquid. So as I said, Sweden and Denmark are the host countries. Between them, they pay about 50% of the construction cost. Our total budget is 1.843 billion euros, distributed over the duration of the construction period, which is about 10 years, roughly. And that money, in a sense, is secured. We have partner countries. Here you can see the flags of all the partner countries, the host countries and everybody else. If you know your European flags, you can work out which countries they are. The other countries then contribute the remaining 50% of the construction budget, and we are still discussing how we're going to share the operational funding. Obviously, the other countries would like the host countries to continue paying 50% when we're operating. The host countries would like the other countries to pay something closer to their share of the beam time that they're going to get once we're operating. And that's a discussion which is ongoing at a high level between the research ministries of the various countries. Welcome to European politics. We have this tension between cash and in-kind. That's what IKC is, in-kind contributions. So most of the countries, apart from Denmark and Sweden, said, okay, sure, we'll give you money, but we're not really going to give you money. We're going to give you people, and we're going to give you stuff. And that would be count as the German or the French or the British in-kind contribution to the ESS. So that's how, and we're getting 70% of the non-host country contributions as in-kind rather than cash. So that means we don't just hire people in Sweden and buy stuff from Sweden. We negotiate with our partners, and they get people at their labs to design stuff, and they provide and they buy stuff and provide it as in-kind contributions. It makes it quite a complex thing, but what it does is it taps into their experience. We have this, okay, I was going to, hang on, I was wrong. So okay, never mind. We have this big network of labs across Europe with a lot of experience in building neutron facilities, and ESS as a facility has only been around a couple of years, does not have any experience, so it's very useful for us to actually have these in-kind contributions from the partner labs. Okay, here's our spending profile. Right, we're now in 2019. If you look at the blue color of money, that's what integrates up to 1.843 billion euros. Right, we've spent most of that already, so even if the countries were to come together and say, we're not going to give you any money for initial operations, that's red, or steady-state operations, that's green, we already spent most of the construction money. And we've secured the initial operations funding for this year and next year, and we are discussing the size of the red and green budgets for the coming years. So in a sense, that's how these big projects work. You can only see that far ahead, and we have secured sufficient funding in order to move ahead. That's the important thing. So we have a lot of money committed. We have a lot of stuff designed and pretty much ready to install, but not that much actual equipment installed yet in Lund. We have a structure. I'm not going to go through that. That's boring. But we have now 600 employees as compared to the 30 when I joined 8 years ago. It's a very international place. We have way more nationalities than we have countries. Partner countries. Basically, we will hire people who have the right expertise, and we don't care where they come from. And as I mentioned, we have something like 100 collaborating institutions, which are spread out over Europe. This was a slide I thought was going to come next. So we have a bunch of different labs, many of them, ICIS in the UK, MLZ in Germany, LLB in France, that have been building and operating neutron instruments for decades and have a lot of experience, and that's what's really valuable for us to be able to tap into. We would not be able to build this without them, even if you could imagine France, Germany, and the UK giving us cash. That would be easier. Yes, it would be easier for us to manage, but it would take us way longer to build up the expertise to build it than being able to tap into what they already know how to do. So this is what our site looked like a couple of months ago. Here is the proton accelerator, right? It's about 700 meters long, so the ion source is there. It's a long linear accelerator. The target station will be there. And then we have the experimental halls here, and they've already almost finished one of the experimental halls off to the side. I'll show you more of that in a minute. And at night time, it looks very Christmassy with a long exposure photo. But it's starting to look like there's actually really stuff out there, which is very encouraging for those of us who've been in the project for a while. And if you're really interested, there's a website you can go, and every week you can see what the progress is on site. So what are we expecting the performance to be like at ESS? I mean, we claim we're going to be world leading. In order to be world leading, you need to start out by having a very bright neutron source, right? Then you have to add a bunch of other stuff as well. That's a necessary but not sufficient condition. So here I'm comparing the expected brightness of the ESS neutron source to other facilities. This is as a function of time. We are pulse sources, as I mentioned. Our pulse is about 3 milliseconds long, right? And it looks like this discharging capacitor shape, right? The proton pulse is on during that time, during which time the neutron, the cold or the slow neutron brightness pumps up to a steady state level, and then the proton pulse comes off and the thing decays again with some characteristic time. This relates to the moderation time of the fast neutrons being converted to slow neutrons between the target and the neutron moderators. And we compare that to the ILL. As I mentioned before, the ILL is the world's currently leading neutron facility. That really doesn't look impressive on this plot. But remember, that of course is a continuous source. So integrated under this line is actually about the same as the integral under this pulse, within a factor of 2. So they have to design the instruments differently. They're not a pulsed source which allows them to use time of flight to determine the neutron energy like the pulse sources I'm showing here. So here I'm showing the ICIS pulses. I used to work at ICIS, so that's a place that I'm very familiar with. They are probably the second most productive scientifically neutron facility today. You wouldn't have thought so by looking at the size of those, but it just shows that, big size isn't everything, right? SNS and JParc are the two newest kids on the block, and they of course look much more impressive than the ILL and ICIS levels. These here I'm showing the peak shape and the level of neutron source brightness that you can get depending on which moderator you choose at the SNS or JParc. So we will get something like that level, so of the order of, roughly an order of magnitude more than any existing facility, depending on who exactly you're comparing to. And then at the moment, it looks like we are only getting funding to build a 2 megawatts worth of accelerating cavities. So to go from 2 to 5 megawatts, we're going to have to take that money out of operational funding, which means it's this blue pulse, which we actually have money to build right now, which we're building right now, but it's upgradable to get to that.
Is it upgradable afterwards?
Oh yeah. In fact, half of the accelerating cavities are being installed to go to 5 megawatts, but the klystrons, the power supplies to feed them, are not installed. Okay, so as I mentioned before, we have this tungsten target, right, 2.5 meter diameter, with the proton beam coming in on the edge, and then above it we have a moderator. So the purpose of the moderator is to slow down the fast neutrons to increase the wavelength so that they can be used for diffraction experiments and study solid state systems. So we have this hydrogenous moderator above. It's actually a combination of liquid hydrogen and water. Liquid hydrogen if you want to have long wavelengths, water if you want to have somewhat shorter wavelengths. When I was talking about long, I'm talking about a few angstroms, so it's tenths of a nanometer in wavelength. And one of the findings that we had about 5 years ago, which is some of the early papers from ESS, was that by reducing the height of the moderator, as shown in this graph here, you can actually increase the brightness. So relative to something which is 10 centimeters tall, which is the height of today's neutron moderators, we could increase the brightness, and in particular for the cold moderator, right, for the hydrogen moderator, you get the significant increase in brightness by reducing the height of the moderator. What happens when you reduce the height of the moderator? Of course, you get a higher brightness, as you can see here, but you get a trade-off. Here is a sketch of a neutron source with different heights, and you have a neutron guide, which is basically a tube with reflecting coatings on the inside, which will transport the neutron beam away, right, out to the instrument. And as you reduce the size of the source, you reduce some of the efficiency of the guide. Because if you imagine you have this geometry of the guide, this ray, this neutron trajectory coming here, it could make it through the guide, except once you make the moderator only this tall, there is nothing coming from there anymore. So what we talk about filling the guide. We're not filling the guide properly anymore once we reduce the moderator height below a certain size. And this can be quantified in a quantity known as a brilliance transfer, which is shown in this curve. So the smaller the source is, the more flatter you make it, the less efficient the coupling is between the moderator and the guide. Right? So the actual amount of neutrons which you transport out through the other end of the guide is actually the product of this brightness and the brilliance transfer. And that has a peak.
That's a trade-off of collimation.
That's exactly what it is, yes. So you end up with an optimum, right? The product of one of these lines and this brilliance transfer. And so you can see for the cold neutrons and for the thermal neutrons, the trade-off is at about the similar moderator height. It's between 2 and 4 centimeters. And so we decided on 3 centimeters for the optimum moderator height. What we've done is, so this has now been fixed to 3 centimeters, and below the target, we were originally planning on putting more moderators for other instruments, but in fact we've decided to put nothing there because all the instruments that we are currently building are perfectly well served by this moderator assembly above the target. So that gives us an upgrade option. One day when somebody has a really bright idea or a need for a different kind of neutron source with a different wavelength spectrum or different time structure or different size, we could build that in there. So there is a lot of upgradability built into this. Here is a horizontal cut through this upper moderator position. It's known as the butterfly geometry for obvious reasons. We have para-hydrogen, liquid hydrogen, in this butterfly shape, and then water insets on the side. So if you have a neutron beam directed towards the para-hydrogen, you will see a cold spectrum, and if you then direct the neutron beam towards, or you direct your point of view towards the water moderator, you will see a thermal spectrum. So you can get different wavelength ranges depending on which part of the moderator you're looking at. So we've designed a system where we have a number of holes in the shielding around the moderators, where all which are oriented along these axes, the beamport axes, all pointing at this junction between the water and the hydrogen sources, so that every instrument that you put there, if you extract a neutron beam exactly along the axis of the hole in the shielding, it'll take half cold and half thermal. But if you shift it, if you rotate it a little bit within the hole in the shielding to one side, you'll pull out a water spectrum, and if you pull it a little bit the other way, you'll pull out a cold spectrum. So it gives you a huge amount of flexibility in where you place the instruments, that every single beamport can give you a cold or a thermal spectrum, which is not available at other facilities. If you look, here is a cut-out view of the moderator assembly at the spallation neutron source at Oak Ridge. This is I believe, a cold moderator. No, that would be the thermal moderator, the water moderator. All the beamports here, they have no choice but to view the thermal moderator, and all the beamports here are viewing the cold moderator, and so on. You get the spectrum.
Sorry.
Sure. Yeah.
What distribution falls out of that slugger?
So the distribution is in the giga electron volt range. It's very high. it's very high neutron energies. So you
On
slow
the
them
spatial,
down.
Is it just
Oh.
a random?
Oh,
small
it's
number?
isotropic to a first approximation. So in order to increase the brightness of the neutron moderators, you embed them inside this reflector material, which is basically a low absorption material, which will prevent neutrons from escaping and will reflect them back into the moderators. That's a basic design principle of these spallation sources. So, as I mentioned before, we have this large pulse width, and compared to a short pulse source, as I was showing before, they have much narrower pulses of the order of 100 microseconds or less compared to our 3 milliseconds. That translates directly into actually a loss of resolution. If you're using that emission time in order to establish what your neutron wavelength is when you're doing time of flight, i.e. you measure the arrival time of the neutron and that tells you what wavelength it has because you know its emission time. If the emission time has an uncertainty of 3 milliseconds, that gives you a much lower resolution than working on a short pulse source. So what we do is we have a device known as a neutron chopper, which sits very close to the moderator and which just opens and closes for a short time. It's a mechanical device. It's a rotating disk, basically. And that means that we can choose our pulse width as we want for any experiment. Whereas if you go to SNS or any other spallation source, you go to different kinds of moderators. I'm not going to go into what this means, coupled, decoupled, poison. There's ways of designing moderators to give you different pulse widths and different resolutions, basically. And if you want high resolution, you basically do it by putting in neutron absorber in there. And yes, you get a better resolution, but you get a big reduction in the peak brightness as well. Whereas when you select the resolution at the ESS using a chopper, you get the full peak brightness independently of which resolution you dial in. And you can do that for every experiment independently. So today, I can choose to run in high resolution mode and pull out this peak. And and later this evening, somebody comes in and they want to make they want flux and they don't care about resolution. We can just use the whole pulse width. So we have a much higher degree of flexibility than existing spallation sources, which is not covered by these gain factors I was talking about before. So we are built to be very upgradable. As I already mentioned, 5 megawatts has now become an upgrade option, right? We've got money to build 2 megawatts. But what that means is we've got all the accelerating cavities in place here, but along them where we put the klystrons which feed the accelerating cavities, we've basically stopped here. We've run out of money to put the additional klystrons in this part here. We are funded to build 22 instruments. We can build way more than that, right? It's a facility which is intended to run for something like 60 years. Our primary upgrade path is to build more instruments on the target station that we have. That's in distinction with other facilities. SNS, for example, where I'm going next week, they have a project to build a second target station. So if you like, they would build another hall like this, adjacent to it, and feed both of them with the same accelerator. That's not what we would do. We would just put more instruments in the same target station. We have a lot of beam ports, right? So we can, in principle, extract 42 beams, even though, but we only have funding to build 22 instruments. We've also designated upgrade areas. So these are areas on the site where we don't build anything which would be expensive or painful to move later on. So we can extract neutron beams in those directions. We could build another hall out there. We could build a really long beam line out there and so on. So we see ourselves as being a facility. One of the reasons why the ILL has been so successful, it came online in the early 1970s and is still world leading, was that it was designed to be upgradable in terms of its instrument suite. The reactor has always operated at the same performance since 1970, but the instruments have improved by probably 2 orders of magnitude since then. And we want to be able to offer that kind of upgradability in the future as well. And a lot of thought has gone into designing ESS to be a long-term upgradable facility which will remain world leading as a result. And as I already mentioned, we have this lower moderator position which is not yet defined. That's another upgrade possibility. We have this flexibility of the spectrum for the cold or thermal neutrons and flexibility on tuning the resolution for the beam lines.
For the N and bar, is it going to be kilometer?
The N and bar beam line, that would be maximum 300 meters long.
300, not a kilometer.
No.
I heard. Okay.
Well, no, out here we have a motorway, which limits us unless you want to do something. You'd have to do something clever.
Build an overpass.
Yeah, there's a motorway at 300 meters or 320 meters. The longest beamline is 300. Okay, so now I want to get a bit more specific about the instruments. Neutron instruments cover a very wide range of spatial and time phase space. Right? So what's shown here is the length scales which are accessible by diffraction or real space techniques. Right? We go from the order from, well, an angstrom, smaller than an atom, up to macroscopic objects of the size of several centimeters using imaging. And there are many other techniques which also access this distance range using X-rays, NMR, optical methods, and microscopy methods. We then also have spectrometers which measure vibrations, and we can look at vibrations from microseconds down to femtoseconds in characteristic time. And again, there are many other techniques which can do that as well, right? Within visible light or X-ray spectroscopy. So you can do some of this science with other techniques, clearly, but you get the unique strengths of the neutrons in those parts of phase space where we can address it as well, as I mentioned before, relating to magnetism, relating to isotope separation, and so on. So each of these shapes is covered by a different kind of instrument. And I'm not going to go through all the different kinds of instruments. I'll just have you believe me that we have a lot of instruments, and they're all these different types. And here you can see the use of different kinds of instruments, ranging from small angle scattering right up to nuclear and particle physics. This was work done by the European Neutron facilities last year. And you can see, basically, if you want to satisfy the neutron users in Europe, you need to provide all these different kinds of instruments because they're all in use. Right? There's no one technique which covers everything. If you look in terms of the geographical distribution, Europe has historically been very strong in this area. That's largely because of the success of the ILL and then ISIS, which came later. So of the global neutron community, Europe is about a half, and North America is a quarter, with other countries then representing the rest. And within Europe, France, Germany, and the UK, between them, account for about 2/3. So they're the big countries that have to be involved as far as we are concerned. So we have a community in Europe of something like 5,000-6,000 researchers producing 2,000 papers a year using neutron scattering. It's a fairly large and very productive scientific community. In terms of the fields which they address, physics is still dominant. Physics meaning is dominated very much by magnetism and structural studies, but also particle physics and other types of fundamental physics, energy materials, chemistry, soft matter, life sciences. There has been a trend, and this will likely continue, to more and more soft matter and life sciences. And that is I'm not showing the change in time, but we expect that this part here is going to be growing increasingly over the next years, and the ESS is designed to be specifically have its strengths in those areas in soft matter and life sciences. The instruments which we are building is shown here, and you can see these same little icons showing the different science areas they address. Any instrument which has a name and is shown on a darker background is an instrument which we are currently in the process of building, that we have committed ourselves to building, and which is going ahead. The ones on a lighter background which don't have names are instruments which we predicted in our technical design report we might build, but we don't yet have the funding to build, and nobody has stepped forward and said we want to build this. So we don't know yet if we're building surface scattering. That means grazing incidence, small angle scattering, right? Particle physics. We don't have anybody building that beamline. We don't have a spin echo instrument. So we have some gaps in our instrument suite. as a result of the fact that at the moment we're just funded to build 15 out of the 22 instruments. So we have these 15 instrument projects going on, covering small angle scattering reflectometry, diffraction, both powder and single crystal, engineering diffraction. We have an imaging instrument. Where did that go? Oh, it's the first one. Yeah. We have 5 different spectroscopy instruments, specializing in different areas. And as I mentioned, we don't yet have a particle physics or spin echo instrument. And they're distributed over the site shown here. At one stage, we had a policy that all instruments had to be named after a Nordic god. That's why we've got things like Odin and Freya. But it being an in-kind, European thing, some people said, "Nah, we don't want to do that. We're just going to call them what we feel like beer." Beer, incidentally, is a Czech-German collaboration, which stands for the Beamline for European Engineering Research. And the Czechs and the Germans decided, what can they agree on? Obviously, they're both good at that. And so there's flags in each of them. As you can see, that's because each one is an in-kind contribution from those countries. Right? Sometimes from a single country, like the Estia reflectometer, sometimes from bigger collaborations, like Bifrost. And they cover all these different types of instrumentation, and the ones shown in bold are the ones which we are building first. We're building 15 instruments at the same time. At the same time doesn't mean they all have equal priority and they all get to go in an uncoordinated way. We have to coordinate centrally. So 8 instruments out of those 15 have priority to go for installation slots, and the other 7 have to wait their turn nicely. This is how that looks on some kind of schematic Gantt chart. There are 15 instruments from the ones that are named up to and including Freya, as a function of time. Blue means the instrument is either in design or in construction. Red means switch the beam on and we're doing commissioning work. And green means we're doing user science with users at some level. So you can see the first instruments go from blue to red in the middle of 2022. That's when we expect protons on target for the first time. So that's when the first instruments will be allowed to take beam and can start characterizing, seeing, fixing whatever problems they find when they do that. Nobody's expecting we can do science immediately in 2022. But I would expect during 2023, after half a year to 1 year of taking data, you would be in some kind of position to actually put in a sample where you don't know what it's going to tell you and get out something scientifically new and publish it. That's a high-level milestone we have. Instruments 16 to 22, we are planning on making a decision. That's what these diamonds are, decision points. So next year we plan to make a decision on which instruments are going to make it into the construction program as numbers 16 and 17, using money from our operational budget, and so on. And in the background, this gray thing you can see is our expected power ramp up to reach 5 megawatts. Okay, so we expect to be at 2 megawatts until the end. Well, you can see the timescale is out to 2030. And I've been talking about upgradability and all that. That means stuff after 2030. This is a long-term project. Right? When people ask me when is ESS going to be finished, finished. That's a relative concept. Right? It's not in my career. Or, I don't know. There are some people here who are younger than me. Maybe in your career. I kind of doubt it. It will continue to be a work in progress for decades, and that's how it should be. So I'm just going to pull out one example, Bifrost, as an example of an instrument which impacts on quantum magnetism, which I thought would be interesting for this community. And it's also a good illustration of the kind of gains in performance that we expect over other existing instruments. So quantum magnetism is very much driven by symmetries, right? And symmetry is driven by dimensionality. Right, and anybody who's done crystallography will know about dimensionality and symmetries. How do you map 2D objects and 3D objects onto each other? And it's of course interesting in a fundamental sense. How does dimensionality and symmetry relate to real objects? We have 2-dimensional objects, but that carry spin and are responsible for magnetism, which are then separated and therefore largely independent and not 3-dimensional. So they behave like 2-dimensional planes, and we only have to worry about the interactions between objects in the plane for this particular compound. This is an iron oxide system. And you can play around with the dimensionality of a problem by playing around with the physical structure of it, with the chemistry of it. And very often the quantum mechanical behavior, which of course results in the shape of the interactions, is strongly dimensionality dependent as well. As an example, if you can take one of these quantum critical points. Quantum critical points means that as you vary the field, as you lower the temperature, you can predict that there is going to be a phase transition, but the phase transition happens at exactly at temperature 0, which you're never going to reach, but you can approach it infinitely closely. And you can predict the various magnetic phases that you're going to get. And the dimensionality changes as you get there. And as you reach this quantum critical point for this particular compound, actually the golden ratio, this 1 plus root 5 over 2, which is a purely geometrical quantity, which you can also see in the shape of this cyclone, I'm not sure if it's a cyclone or a hurricane, pops out, which is reflected by the energy level differences as you approach this quantum critical point. So studying quantum magnetism has fundamental applications in terms of symmetry, but of course it also has societal applications in terms of being able to make devices which can do stuff we want them to do. Another low-dimensional effect is a high temperature superconductivity. I mean, we've had these regular superconducting compounds like lead, niobium, and so on, which go superconducting at helium temperatures for many, many years. We then had this breakthrough in these copper oxide-based superconductors in the 1980s. There is always the hope that eventually we'll be able to reach a superconductor which is still superconducting at room temperature. And there's a huge amount of effort going into developing this, and neutron scattering has been fundamental in developing this, these materials. Obviously going through the liquid nitrogen temperature, which happened in the early 90s, was a breakthrough for these materials. And this is entirely dominated by its dimensionality. These are layered compounds, they're 2D compounds, the copper oxides. So they're seen, there's 2D grids of magnets, and you can play around with the doping level so you remove spins and thereby affect the interactions between the nearest neighbors. And you can then affect the spin by applying pressure or chemical doping to explore how the interactions are taking place between them. So the superconducting mechanism that's happening, and what you need is you need to couple two electrons so that they can fall into the superconducting state. You can create a Cooper pair. And the conventional superconductors did this by coupling via a lattice vibration, a phonon. And these new high temperature superconductors look like they're, I would say the theory is still not fully established, even though a lot of progress has been made. It looks rather clear that they are being, the coupling is mediated by magnetic excitations rather than structural excitations. And it changes the symmetry, or there's a different symmetry to that coupling than a lattice vibration. So there's a huge amount of work going on in looking at magnetic excitations using neutrons. And neutrons are really the best way of measuring magnetic excitations. We're responsible for this Cooper pairing. In a sense, that is the bulk science case for this kind of instrument, is the magnetism related to superconductivity. You look at, you come in with a neutron, you create an excitation, right? You spins processing in some way, you've added kinetic energy to that, and that mediates the coupling between the electrons, which needs to condense into the zero momentum state in order to create the superconductivity. And there is, and the physics of the coupling is actually, you can extract it quantitatively using neutron scattering in a way which you basically can't do with any other technique. There is a problem, of course, the flux limitation. Neutron sources are extremely dim compared to photon sources. What I'm trying to show here is basically, you're shining neutrons out in all directions. By the time you get to a reasonable distance, you've lost a huge amount of neutron flux. So that the cross-section of the neutrons is proportional to the number of atoms in your sample, which means typically we measure huge crystals. I mean, most crystals can't grow that big, but if you can grow them that big, that's what you would bring to do a neutron experiment today. And then you have the size of the spin that you're trying to look at, and then the physics, right? That you're trying to, which is the interesting thing, is what is this? What is your the mechanism you're trying to explore? And you have two kinds of experiments, two kinds of instruments, right? You can either the workhorse ones where you work with huge, hulking big samples like that, or you're working on something where you either have inherently small signals, or you're looking for small moments, or you're not able to make giant crystals, or you want to measure at high extreme environments, large magnetic field, low temperature, high pressure. And this is the science case of Bifrost, this particular instrument that I'm pulling out. If you look at today's instruments, the flux in the reactor, let's say at the ILL, this is the neutron flux, 10 to the 15 neutrons per second per square centimeter. It's a big number. It looks impressive. Once you've pulled out a beam from that reactor and you've monochromated the beam so that you have a single wavelength, so you know what your neutron energy is and you can actually interpret your data, you've lost 7 orders of magnitude and you get roughly 10 to the 8 neutrons per second per square centimeter in the beam that hits the sample, which means that by the time it's hit the sample and you detect it, you typically get of the order of 1 count per second. Right. So these are long experiments. And you have 2 different ways of doing it. You can run with a triple axis spectrometer or time-of-flight spectrometer. I'm not going to go into the details. The bottom line is, in both cases, it takes about a week to do a measurement like this at today's facilities, if you want to push the boundaries by measuring difficult systems. And in many cases, if that means it's really on the limit of what you can do, and in some cases, many cases, you get no result because the signal is too small. You can't, if you get your calculation wrong and it turns out, oh, you don't see a signal in a week, you need 100 weeks, forget it, right? You're not doing the experiment. So this is where the power of the ESS comes in. If we can boost this compared to the ILL by 2 orders of magnitude, that's obviously a game changer in that area. And that's the flux on this instrument is 10 to the 10 as compared to 10 to the 8, as I was saying before. So 100 times more flux than any existing instruments, and about a factor of 30 compared to the world-leading instrument today. In addition to that, the back end of the instrument design is very cleverly optimized, and this comes into the neutron optics. It has this array of analyzers which sit in an equatorial plane around the sample, which gives you another factor of 10 advantage. So overall, it's a 3 order of magnitude increase in counting rate. From the sample sits here, right? This is a neutron, scattered neutron hitting a graphite crystal and then being diffracted down to a detector, and we have an array of crystals behind each other. Each one is partially transparent. So this kind of concept, when you combine the neutron source with a new kind of instrument, you can get this 3 order of magnitude increase in capability, which is going to be groundbreaking. And it's really optimized for extreme sample environments. So you have a picture of putting it in a high field split coil magnet, which is what you need to do in order to gain traction in the scientific field. It's really optimized for looking at the scattering, which can make it out through the very small opening in a split coil magnet. It's also, so that means you'll be able to open up the field of high TC superconductors. It means you'll be able to look at crystals which are simply too small to see today. You could measure crystals of the order of sub-cubic millimeters or even smaller. For instance, ones that have to work at high pressure, where you simply can't pressurize something which is cubic centimeters in size in order to get to the interesting high pressure phases which are showing the effects you're looking for. Or you could even look at thin films which provide magnetic properties which don't produce huge amounts of heat, which is the problem with many of the materials that we have today. So that was just one example. To summarize, we're looking then to produce breakthrough performance by increasing the brightness, by increasing the flexibility, and by having the best instrument designs. We have a large and very scientifically active community in Europe. We have ongoing discussions with prospective partner countries, including Canada. We had a visit from a Canadian delegation last year who were exploring options of joining ESS. What it looks like at the moment is that Canada may end up joining ILL rather than ESS initially, which is the logical thing to do in order to get access to neutron beam time and ILL, and then join ESS in another step. It's built by the European labs, and first science expected in 2023, but as I mentioned, this is a long-term thing. Okay, thank you.
We asked a lot of questions, but just small comment. Kind of Canada was one of the frontiers in the study of this neutron research. Brookhouse, for example, is one example.
Yeah, right.
To get a Nobel Prize, and the sad part that the reactor is coming down closed here, so we don't really have any other facilities to join, kind of nowadays. And any other questions left? Yes.
So this
Yeah.
is specifically for the Bifrost instrument, but it
Yeah.
really applies all over. You mentioned you can do different magnetic fields and different pressures, yeah?
Yeah.
So those are devices, like a pressure chamber or magnetic field that you
Yeah.
build in yourself, or are you leaving room for configuration, for example, changing the directions you need for magnetic fields?
Okay, so for the magnetic fields on Bifrost, it's designed, let's see, it's a bit hard to see here. So it's been designed to leave enough space for, the current state of the art is about a 15 Tesla split coil magnet. That's about the biggest you can buy off the shelf today. It looks like, with the hybrid high TC, low TC superconducting magnets coming out of Tallahassee and CNRS in France, you can probably go to the order of 25 Tesla in the next 3 or 4 years. And the instrument is designed so that there's a big enough envelope around the sample area that you can install one of these. So we have the funding for a 15 Tesla magnet, and we have the space for 25 Tesla magnets whenever that's available, and we get the money to get one.
And then you'll put in just some kind of, will it be a closed chamber pressure system or something like that, or just an anvil?
Well, we have a range. I mean, I didn't go into the sample environment group. It's going to make available. We have diamond anvil cells for the highest pressures, right? And then a whole range of other different kinds of pressure environments for lower pressures. Yeah.
You mentioned there's a chopper. Is that common to all beam lines, or you have a chopper for every beam line?
No, you have one for every beam line. Yeah, at least one. Most instruments at ESS have several choppers. Yeah.
Yes. In concluding, I just want to say it would be great to have some brute force source when you increase several order of magnitude intensity, not worry about any smart and simple way of doing it. It's not the case, but luckily
No.
we're addressing all the spectrum to increase tremendously the amount of neutrons at the detector.
Yes. Yeah, that's what counts, right? It doesn't matter what's coming from the source. If it doesn't turn into a high count rate, it's not useful.
I guess it was appreciated to me when people say NIST, which is a 20 megawatt reactor, they usually put a slide. So if you compare it to the light source, it will be equivalent amount of photon produced as a the Christmas light bulb. The amount
Yes.
of neutron produced is the 20 megawatt reactor.
Yeah, that's about right.
Okay, let's
Yeah.
thank our speaker again. We have no
Hey.
questions.
Hey.
Thank you so much
Thank you.
for coming in.